Hi guys, welcome back to my channel. Today I want to talk about a really high yield organic chemistry concept, and then which is electron withdrawing groups versus the electron donating groups. And I also want to connect this idea with some other organic chemistry concepts. All right, let's jump right into this. Okay, so I'm going to first list some common electron withdrawing group and electron donating groups. And then I will tell you a trick to quickly differentiate which one is electron withdrawing group and which one is electron donating group, okay? Maybe a trick that you've never heard of. Okay, so first, so I listed 3 tiers. So the green tier is the weakest electron withdrawing groups. They're the, whatever compound it is, it's an R that connects to the any halides, right? It can be chlorine, fluorine, bromine, iodine, right? All the halides on group 17 on the periodic table. So electron withdrawing group means those halides, they weakly kind of withdraws electron density from the R group, right? They kind of want electron density. They crave electron density. So they want to try to get it from the R group. And then the second tier, the orange ones, are the R group connected to a carbonyl group, right? You can think of this carbon being electron positive, right? It's a common electrophile that's being attacked, and this oxygen is the partial negative, so that this partial positive carbon, of course, it would crave electron, want to withdraw some electron density from the R group that it's connected to, right? Okay, so the last tier is the strongest ones. Okay, they really want to get the electron density from the R group. Okay, so especially the last one, like you see here, nitrogen is connected to four nitrogen is having 4 bonds, right, connected to 4 things, so that it gives it a positive 1 charge. So a thing with a positive 1 charge, of course, it even craves electron density more than these partial positive carbons, right? So which makes it a really strong electron withdrawing group. Okay, all right, so let's go over the electron density groups really quick. So electron donating groups. So electron donating groups, you can see like this, the first tier, this first green one, the R is connected to 1 hydrogen, right? So there are just 2 electrons like in between them. So it really slightly, just really weakly donates electron density to the R group. Okay. And then also the alkyl group, any alkene chains, okay, no matter how long the chain is, it also donates electron density to the R group, right? And then the longer the chain is, the more electron density it has. Actually, it donates more, right? Okay, and then benzene is also a weak electron donating group, okay? And then we move on to, so these are not, I would not say they're connected to a carbonyl group, like the case here in the orange part here. I would say these are groups rather than carbonyl groups, because I would think they're ester group, right? And then the second one will be the amide group, right? But you might wonder, okay, then what's the difference between this and that? They both look like ester. Okay, I'll talk about that in just a second. Okay, all right. So let's move on to the electron donating groups. Okay, so the blue ones are the strongest electron donating groups. They're the ones that are most likely to contribute their electron density to the R group. Okay, alrighty. So you may find it difficult to memorize, right? Especially, okay, NO2 is the electron withdrawing group, and NH2 is the electron donating group. You can, your memorization can really be messed up during an exam, right? So let me just tell you a trick I've been using to quickly identify electron donating group and withdrawing group, okay? So, I mean, this one is easy to memorize. This one is easy to memorize, okay? And then let's talk about the orange ones and the blue ones, okay? So as you can see, like this R, so it's connected to carbon, right? And then the carbon connected to the oxygen and whatever that the R prime group is. So you can see that this central atom that's connected to the R group, carbon, it really has a less electronegativity than oxygen, right? Oxygen has a 3.5 and then carbon has a 2.5, okay? So this makes the carbon partial positive. So it would want to withdraw electron from the R group, right? And then you can see the same trend if I have an R group, and then this is my nitrogen. Okay, I'm talking about this one now. And then you have a okay, so this is the Lewis structure. Okay, of this compound, and then you would see, okay, this nitrogen that's connected to my R group, nitrogen's electronegativity is a 3.0. I mean, you don't have to memorize the electron activity values because you know the trend, right? You kind of know. I'm just showing you the numbers to give you a visual, presentation, but you really can. No, you really know. The periodic table is provided during MCAT, so you really know like which one is more electron negative, right? Okay, so the oxygen is 3.5. Okay, so you see this nitrogen and this oxygen, the nitrogen is like a less electronegative. So right, the polarity goes this way. So the nitrogen has no other way to get the electron density. Nitrogen wants electron density too, right? It's not as craving as electron does, but it still have some craving. So it would want to withdraw electron from the R group, right? Whereas it's the other case for electron donating groups, okay? So if you look at oxygen here, oxygen is connected to my R, right? So oxygen has 3.5, right? And then the next atom is not oxygen. The next atom is C, it's carbon. So carbon is 2.5, right? So this oxygen is actually pretty satisfied, if you will, right? So okay, I'm pretty satisfied. I mean, between me and carbon, I'm already having the more electron density since I have a higher electron activity value. So there you go, R group. I'm donating electrons to you. Okay, so electron donating group. Whereas, let's look at that one. Okay, so this R group is connected to what? To carbon. And the carbon, 2.5. Oxygen, 3.5. So is this carbon the closest atom to my R group? Is carbon satisfied? No, right? Because the electron density goes that way, goes to the oxygen. So carbon's like, oh, then I have to withdraw electron density from the R group. Okay, so that's how you can. I mean, a more straightforward way for you to recognize and not to mess up your memorization about, okay, which is electron withdrawing, which is electron donating group, okay? I hope that helps, okay? So let's do another example. So like this R connected to carbon and then nitrogen, right? So carbon is 2.5 again. Nitrogen is 3.0. See, nitrogen is winning the race. So carbon's like, okay, I'm going to withdraw from the R, okay? And then let's do one more example. This R, and then the NH2, right? So nitrogen is 3, and then the electron activity value for hydrogen is just 0.1, right? So see, nitrogen is satisfied in terms of its relationship with hydrogen. So, okay, I would donate some electron density to the R group, okay? So for R group, this NH2 is a donating group. Electron donating group. Okay, I hope it's clicking. All right, so yeah, so this is, I think it's a good way for you to look at an electron donating group versus electron withdrawing group, okay? So now let's talk about acidity, okay? So if I have this thing, okay? I'm connected to electron withdrawing group, okay? Versus this thing is connected to electron donating group, okay? So I'm asking you, let's say this is compound A, this is compound B, okay? So compound A and compound B, which is more acidic? Or I say which has a lower pKa, right? Same thing. MCAT prefers to be less straightforward. It might ask you, oh, which one has a lower pKa? It's asking you which it has more acidity, okay? So which one? So we know that from organic chemistry courses, so to tell the acidity of a compound, we want to see the stability of its conjugate base. So, right, so let me turn this into the conjugate base, okay? Conjugate base, CB, okay? So the conjugate base is this, right? After the base grabs the proton, right? So you become O negative, and then this is electron withdrawing group, okay? And then this guy is like that. The conjugate base, CB, is like O negative, and then electron donating group, okay? So we're gonna see which conjugate base is more stable than which has more acidity, right? Which is more acidic, which one is more willing to lose that proton and be turned into conjugate base due to the more stability of the conjugate base, right? So which one? So let's look at this. So this is O negative, right? O negative. So do you think electron withdrawing group is going to provide more stability or the electron donating group? Okay, I'll give you 2 seconds to think about this. Okay, 2 seconds is up. Okay, so of course it is the electron withdrawing group that does a better job at stabilizing this conjugate base, right? Okay, because oxygen is already negative. It's not a partial negative, it's a full charge, right? So if you still donate more negative thing to the system, it overwhelms it, right? If you're kind of withdraw the electron density from here, then the molecule is happier, right? You basically you are providing some positivity to this case, right? Okay, so this conjugate base is more stable. So which means what? Which means I'll use a different color. So which means the compound with the electron withdrawing group has a more acidity, which equals to lower pKa. Does that make sense? And then this guy has less acidity, which means higher pKa or lower Ka. Okay, same thing. All right, so that's the first thing I want to connect, okay? How does electron withdrawing group and electron donating group, how do they affect the acidity differently, okay? How do they affect acidity to different extent? I should say that, okay, to be more precise, okay. And then secondly, let's look at the electrophilicity, okay? So let's say I have a thing here, okay, which is an electrophile, and then I have electron withdrawing group connected, compared to I have electron donating group that's connected, okay? So this is an electrophile. So do you think? So I have a nucleophile here, okay? So the nucleophile is gonna attack my partial positive carbon to do some nucleophilic substitution, all right? Which one? The case of A or the case of B, which one do you think the reaction is gonna happen faster? Of course, it is what? It is the case of a electron withdrawing group that's being more reactive to this nucleophilic substitution reaction, right? Versus the electron withdrawing group, AKA electron withdrawing group makes this a better electrophile, right? And then this is less reactive. Make it a worse electrophile. Okay, this is called the electronic effect. Okay, this is a listed AAMC MCAT content. Okay, all right. So do you guys get why? Why this will be more reactive? Because really, electron withdrawing group, it kind of like withdraws electron density from this part, right? So which makes this is even more partial positive. So let me write this, more partial positive than this, okay? A bigger partial positive than this partial positive, okay? So this makes it a better electrophile and then more reactive, okay? Oh, there. All right. Lastly, let's talk about which one, if it's the electron withdrawing group or electron donating group that makes a better leaving group, okay? So, well, from the second point we discussed, of course, you know, okay, this reaction is more reactive. So, of course, electron withdrawing group makes better leaving group, okay? And then the electron donating group makes poorer leaving group, okay? So here, does it click? I'm connecting the ideas, okay? All right, so now let me clean this up a little bit. And then we're gonna do a problem, okay? Which is MCAT style. All right, so it's tricky. It's not really easy, okay? But it's okay. So here I have two compounds, okay? So I'm asking you, which one is a weaker base? Okay? All right, I'll give you 5 seconds to think about this, or you can pause the video and take as long as you want. All right? Okay, time's up. All right, so very quickly, we can use the trick. So if it was me, I would say, okay, this is a carbon and a fluorines, right? So carbon is like this is super electronegativity. This is a very partial positive due to the fluorine, so that I wouldn't want to withdraw electron. Okay, so this is an electron withdrawing group. Okay, whereas carbon and hydrogen, hydrogen is less electronegative negative than carbon. So carbon is not that electron negative. So I would say carbon is donating the electron density to this. So here, see, CH3, it's an electron donating group, right? All right. So according to this, we can tell that, okay, this is more acidity, right? This is more acidic, I mean, so this is more acidic, which makes it what? A weaker base, right? Does that make sense? So more acidity, and then 0.1 prime, more acidity is less basicity. Okay, and then here, 1 prime is more basicity. Does that make sense? Okay, so that makes this a weaker base, right? Okay, I hope it's clicking. Okay, so this is what I want to go through today, and then make sure you, I hope you can watch the next video, okay? Which I'm gonna rank the all the different alkyl groups acidity. All right, see you soon.